This is the first video review for preparation of your midterm next week. This video will focus on Unit 1, which is the Introduction to Chemistry. This unit started with a focus on introducing you to laboratory equipment. There are a total of 13 different items we talked about and used in class throughout the semester, and you are responsible for knowing the functions of these. First, you have a funnel, which is a glassware that's used to help transfer chemicals, often liquids. You have tongs, which are used to remove hot objects from either a ring stand or a hot plate, or can be used just generally to help transfer objects from surface to surface. A thermometer is used to measure temperature. A graduated cylinder is a glassware that is used to measure liquids. A test tube holder is, as the name implies, meant to hold a test tube, particularly when heating a substance within the test tube. A balance measures the mass of a substance. A crucible is a small ceramic cup that is used to melt substances. A watch glass can either hold small samples or can be used to cover a beaker. A stirring rod will stir a solution. A ring stand will act as an anchor or hold other laboratory equipment. A beaker is the most common glassware that's used throughout chemistry, and this is used to either heat substances or combine substances. A scupula is used to transfer solid chemicals. A striker is used to start fires. And a Bunsen burner is a way to heat objects with an open flame. Now, chemistry itself is the study of matter and the changes that it undergoes. And like all other sciences, we use the scientific method as the basis of chemistry. And as just a review, a scientific method is a systematic approach to study science. According to your textbook, there are 5 steps. The first is an observation. This can be based on anything at all. A scientist will just make some sort of observation. And based on these observations, they ask a question or propose a problem, which is the second step. The third step is to create a hypothesis based on the question or problem, and it's meant to answer that problem or question. Then an experiment is conducted to test the hypothesis, and finally, in the 5th and final step, you come to some sort of conclusion where you accept or reject your hypothesis based on the results of your experiment. Now, if you reject your hypothesis, you basically kind of repeat the last 3 sections of this diagram as shown to get to a place where you will accept the hypothesis and you can move on from there. So often, scientific method can be trial and error. Now, a couple of things about scientific method. The first thing is the hypothesis, as I mentioned. Well, that is a tentative explanation for what you've observed. In other words, we call it an educated guess. There are 2 variables that you have associated with an experiment. The first is the independent variable. This is what is changed based on what the experimenter does. So if you're given an example, you look for what's changed. The dependent variable is dependent on what you change, which is the independent variable, and often this is the measured aspect of the experiment. So that's an easy way to identify the dependent variable. The control is what we use as a standard of comparison. You can have either a control group, which is what your alternative groups are compared to, or you can have a condition that is consistent through all of your different groups and throughout your experiment. Your conclusion is the last step of the scientific method, and this is based on your results. The conclusion can develop into 2 things. It can develop into a theory, which is where you would accept your hypothesis, and you would use other experiments to support it to develop some sort of explanation for a phenomenon. So an example of that would be evolution. There have been many parts of the evolution theory and many experiments to help support that. And then a step further from that is what we call scientific law. This is where a theory has been tested multiple times by different people with several experiments, and it's basically always held to be true. An example would be like gravity. And so in the scientific community, we call this a law, basically saying that it's not going to hardly ever change. Not that it won't, but that it probably can't be changed. Alright, so let's talk about how do you identify some of these terms. So here's an example. Your friend tells you that premium gasoline gets better gas miles, so you want to test the different octane levels in gasoline and their gas mileage performance. Meaning you want to see how much gasoline, how many miles you can get based on the gasoline. You fill your tank with regular gasoline and drive until it runs out of gas and recording the total mileage. You then repeat this process with the same car, but instead you put super gasoline in for one time and supreme gasoline for the third time. So in this example, what is the hypothesis, and what are the independent, dependent, independent variable, dependent variable, and control? Well, the first sentence tells you the hypothesis. It's an educated guess. It's a observation or an explanation. She says your friend, he or she says premium gas gets together better gas mileage. That's what you're testing here. So what is being changed? That's our independent variable. Well, what's being changed is the type of gasoline. The dependent variable is what we're measuring. It's what is dependent on our type of gasoline. That is the total miles driven, or the total mileage. And then finally, our control, that's what's kept constant through all of these. And in this case, it's the car. If you're looking at another way to look at this, if you want to have like a control group, you can use like regular gasoline as your control group. Alright, in an experiment, you have two types of data that you can collect. You have qualitative data, which describes something. It can be the color, the odor, the shape, some sort of other descriptor is a qualitative data. So smell, size, color, those are a few examples. Quantitative data is a numerical information that you collect. This can be mass, height, it can be a calculated value like density, speed, things like that nature. So if you look down here in the bottom, the picture on the left would be qualitative because it describes the different colors, and the picture on the right is quantitative because it's a graph showing numbers. So qualitative describes the quality, quantitative describes the quantity. And that's a simple way to distinguish between the two. Now, with any set of data, you need to be able to interpret your data and see if it's any good. And we have two ways of doing that. One is the precision. This is how close are your data points to one another. And we can use standard deviation to tell how good our precision is. The other thing is accuracy. And that's how close our value is to whatever is considered the accepted value. And we use percent error to determine how accurate we are. Percent error is calculated by taking the absolute value of the experimental value minus the accepted value divided by the accepted value times 100. Now, the main thing is we won't deal with negative percent errors, so if you have a negative difference in the numerator here, you ignore that sign. This is one of the formulas that will be given on your midterm. So, let's look at an example. 4 students measured the mass of one 5.43 gram sample 3 times. So basically they took this one sample that is known to be 5.43 grams and they measured it 3 times. The results of the students are shown below. That's what's in here at the table here. Which student is the most accurate and which student is the most precise. So in this table, they give you each trial for each student. They give you the average here for each student, and they give you the percent error. So, to determine the most accurate, you would want to look for the most, um, you would want to look for the one that has the lowest percent error, or the one that's closest to the 5.43 grams. Well, in this case, our student 1 has a 0% error, so that means that they would have they would be the most accurate. Again, student 1 has the lowest percent error, so they are the most accurate. Now, precision. You can use standard deviation, which in this case they don't give us. The other thing we can look at is we can look at the data sets and we can see how close each one is to one another. So in this instance, let's change to, let's say, blue. We have 4 students. So student 1 has 5.43, 5.44, 5.43. These are all very close together. They're within 0.01. Student 2, looking at these numbers, are very, very far off because you have 2 that are about 5.4 and 1 that's about 6.4. Same is the case with student 3. However, we go to student 4, you have 6.86, 6.86, 6.86, 7, excuse me. So these 3 are very, very close together. So in this instance, we actually have 2 students that would be considered precise because they have the closest set of data. Now, if we were looking at standard deviation, you would look at the one that had the lowest standard deviation, or the one closest to 0. So 0 is always a good thing with looking at percent error and standard deviation. Alright. To show the accuracy or the precision of, actually in this case, the accuracy of a measurement, we have something we call significant figures. And the definition of significant figures is all known digits plus one estimated digit. This essentially shows what the uncertainty in your measurement are. And it's kind of weird to understand how to figure out the number of significant figures, but a couple things, a couple rules that we need to go by. First thing I'll say is that each of these numbers we're dealing with are a measurement, so you can't really assume there's a decimal there, that there's extra zeros there. You just have to deal with the numbers that you're given. Again, you have to imagine these are actual measurements, so there is going to be an uncertainty in the measurements. So how do we tell whether something is a significant figure or not? There are 4 basic rules. 1, anything that's not a non-zero number is always considered significant. Now, what does that mean? That means anything between 1 and 9. Okay? An example here would be 495. And in this case, we would have all 3 digits would be considered significant. That's another point I want to bring up, is we're looking at the individual numbers in a measurement to figure out which one is significant or not. So we're counting each digit individually. Our second rule is that zeros between non-zero numbers, again, those are numbers between 1 and 9, are always considered significant. So if you have the number 104, in this case, again, we have 3 significant figures because this 0 in between the 1 and the 4 is basically sandwiched in between non-zero numbers, so it counts. All final zeros to the right of the decimal are significant. What this means is if we have a number of like 10.10, the 0 furthest to the right here is going to be significant because it's after the decimal. Basically, any number after the decimal that follows a 1 through 9 number is considered significant. Finally, any placeholder zeros are not significant. So what this means is if we have like 1,000, 1,000 only has one significant figure in this case because these 3 zeros are just holding the value of the number. The other way you can see it is if you have 0.001, this again only has one significant figure because those zeros in front of the 1 are just holding the value of the number. Now, the only tricky thing that happens is if we have a decimal at the end of a large number. What this means is that, let me change my color real quick, that if we have 1,000 here with a decimal here, that changes it from one significant figure, like as shown here, to 4 significant figures. I don't know why they devised this, but that's just how the rules work. It's meant to show what, how certain you are about measuring it. The difference is in the first number here, where the asterisk is, you only are certain to the thousandths place. But in this other one, where I've shown the decimal, you're certain to the ones place. You are certain that it can measure out to 1,000 all the way to the ones place. So I think that's the reason why we developed this, was so that way we could show our certainty. Alright, so let's look at an example. Determine the number of significant figures in 40,030 grams and 0.000010 liters. Alright, so the first one, looking at 40,030 grams, we have a 4 and a 3, which are significant. We have 2 zeros that are sandwiched between the 4 and the 3, which are significant. And we have a 0 at the end with no decimal. So the 0 at the end doesn't count. The ones that I've underlined are all significant, so in this case we have 4 significant figures. Alright, and let's look at the next one. So we have 0.000010 liters. Alright, so all of these zeros in front are just placeholders. The 1 counts. The 0 on the very end counts because it's after a 1 through 9 number, and it's after the decimal. So in this case, we have 2 significant figures. Again, this is kind of tricky, but you just have to remember these are actual measurements, and we're using them to show the certainty of our values. Now, when it comes to doing calculations, we have 2 groups of calculations we're going to deal with. We're going to deal with addition and subtraction, and when you're dealing with addition and subtraction with significant figures, you do the calculations like you would normally. But then you round to the last common decimal. What that means is that you round to the last place furthest to the right that these values have in common. So let's look at our first example down here. We're going to kind of jump ahead. This is complete 52.6 grams plus 309.1 grams plus 77.214 grams. So if we look at this example, a lot of times it helps if we write these vertically, so I'm going to write it vertically over here. So 52.6, 309.1, 77.214. Okay, again, these are all grams. So if we line them up, you can see here that the placement after the decimal, the tenths place, is the last place furthest to the right that these 3 numbers have in common. It's the last place we are certain that these all will have a value. So we calculate it like normal, and when you do that, you get 439.914, but we round to the tenths place, which will give us an answer of 439.9. So with addition and subtraction, you round to the last common placement furthest to the right. And this really helps to do vertically so you can visually see where the last place that they all line up at. Multiplication and division are different. In this case, you figure out how many significant figures each value has, and you're going to round to the fewest number of significant figures. So again, going back to the example, we have 529.31 meters divided by 0.90000 seconds. Alright, so if we look at this example, this first number here is all non-zeros. So that means we have 5 values, or 5 significant figures. The second one, this first 0 does not count, but all 3 zeros after the 9 do count. So in that instance, that gives us 4 significant figures for this seconds measurement. So what this is going to do is we're going to round to 4 significant figures. So we're going to go ahead and do our calculations, which gives us an answer of 588.1 and some numbers. And then we're going to count from the left to the right 4 significant figures. 1, 2, 3, 4. All of these are non-zero. In this case, our answer does have 4 significant figures, and we don't have to really round. So again, with multiplication and division, you round to the lowest number of sig figs based on what your numbers that you're multiplying or dividing are. Alright, now when we're doing math in science, sometimes we come up with very, very large numbers or very, very small numbers. And scientific notation is something that was developed to help manipulate these numbers and to represent these really small or really large numbers. The basic setup is you're going to have some sort of coefficient between 1 and 9 multiplied by 10 to some x value. If your x is positive, then you're going to have a number greater than 1. If your x is negative, it's going to be less than 1. Or, excuse me, less than 0. Positive x is greater than 0. Negative x is less than 0. So, in this case, we have two values in the example. 50,000 meters per second and 0.000023 seconds. And they want us to write in scientific notation. So, the best way to do this is for a positive, or for any one, you basically find the first number, in this case 5, and we're going to put a decimal between it and the next number. Okay, and our next number is 0. So we're going to write 5.0 times 10, and then we're going to count how many places to wherever the decimal is now. So 1, 2, 3, 4. So because this is greater than 0, it's going to be a positive 4. So 50,000 meters per second becomes 5.0 times 10 to the 4th meters per second squared. The other way to do it is I just count zeros. So you can do 1, 2, 3, 4 zeros, and that's our exponent. Now the opposite way, with a small number, again, you go between your two numbers, two non-zero numbers. So in this case, 2 and 3, we're going to put a decimal between them, so it becomes 2.3. And this time I'm just going to count the zeros after the decimal here. So it's going to be 1, 2, 3, 4, and then we count, because the decimal is after the 2, we count the 2 also, so it becomes 2.3 times 10 to the negative 5th. We can also go 1, 2, 3, 4, 5. We've moved the decimal up 5 places to get to where it's 0. So again, if it's positive, it's a large number. If it's negative, it's a small number. Alright, when you're adding and subtracting or multiplying and dividing with scientific notation, it's a little different than normal numbers. Addition and subtraction, you have to have the exponents be the same value. And you can move the decimal to make the numbers go up or down. If you move the decimal to the left, your value of your exponent gets bigger. If you move it to the right, the exponent gets smaller. Okay. So, with addition and subtraction, your exponents have to be the same. Then you simply add or subtract the coefficient, and you place your 10 to the x value on the end, because the exponent is the same. So, let's look at our example down here. We have the problem 1.2 times 10 to the negative 4th plus 4.7 times 10 to the negative 5th. Alright, so what we need to do is we need to put both of them to one value. I typically pick the larger value. So in this case, because it's negative value, the smaller the negative, the larger the number. So we're going to make both of them 10 to the 4th. So with the 10 to the 5th one, we're going to move it one decimal to the left, which will increase the value to negative 4. And it becomes 0.47 times 10 to the negative 4th. Another way to check is because we know negative 5 is smaller than negative 4, the coefficients, once they're the same, should be smaller. So 1.2 is larger than 1.4. So now we just add our coefficients. 1.2 plus 0.47 gives us 1.67. And then because they're the same exponent, it's times 10 to the negative 4th. Multiplication, we don't have to worry about the exponents. All we do is we multiply the coefficients, and then we add the exponents. Division is the same. You divide the coefficients, and then you subtract the exponents. So for multiplication, you're going to add the exponents, and for division, you subtract the exponents. And the main thing to keep track of is when you're subtracting them is to make sure that you take into account that two negatives, like a minus a negative, is a positive. So like if you have an example of 4 minus, let's see here, get rid of that. So we have an example of, let's say for instance, 4 minus negative 3. Well, that's actually 7 because it becomes, these two negatives cancel out and it becomes positive. Alright, so our example here is 12 times 10 to the fourth times 5 times 10 to the negative second. So we take 12 times 5, which is 60, which is here, 4, and we subtract 2, so this should be 10 to the second, excuse me, which is actually incorrect in the PowerPoint. So, so again, 12 times 5 is 60, then we say 4 plus negative 2, which should give us 10 to the second. So the answer here is 60 times 10 to the second is the correct answer. Alright, finally, the last bit of math. In science, we have the metric system, and this helps us convert between units very easily. There are, I believe, let's see here, 1, 2, 3, 4, 5, 6. I think there were 9 prefixes that you need to know. We have giga, which is 10 to the 9th, mega, 10 to the 6th, kilo, which is 10 to the 3rd, hecto is 10 to the 2nd, deca is 10 to the 1st, deci is 10 to the negative 1st, centi is 10 to the negative 2nd, milli is 10 to the negative 3rd, micro is 10 to the negative 6th, and nano is 10 to the negative 9th. Remember that going between each of these is a factor of 10. So if you're converting things, you need to make sure that you realize that if you're going from deci to milli, that's actually 100 because it's 2 sets of 10. There's 100 milli whatever in a decimal whatever. And we have 5 basic measurements that you'll use. Time, your base unit is going to be seconds, so gigaseconds, megaseconds, whatever. Length we typically measure in meters. Mass, the base unit is kilogram. Temperature is Kelvin. Remember me talking about the fact that Kelvin was developed so that way you have no negative values. To get between Celsius and Kelvin, you just add 273. And then finally, volume will be measured in liters. So in this case, you need to make sure you know your prefixes. Now, the way to convert logically is called dimensional analysis. And the way we do this is we use things known as conversion factors. These are equivalent ratios that allow us to convert units. And the trick to this is to convert or to line up our conversion factors in a way that our units cancel out. So here's an example. Mount Everest is 8,847 meters high. How many centimeters high is the mountain? You start with the value they give you over 1. So in this case, we have 847 meters. We know, if we go back a slide, that here is our base, which in this case is meters. We know that centi is 10 to the second. Well, like I was talking about, that's 2 below where we want to go to. So we know that 1 meter is 100 centimeters because that's 2 placements below, meters bigger, that's 2 placements, so that's 10 times 10, which is 100, below where we start. So we use the idea that 1 meter, which will go on the bottom here, is equal to 100 centimeters. So this will allow us to convert between meters and centimeters. So again, meters go on the bottom because, as I've marked out here, we want these meters to cancel out. So if it's on the top and on the bottom, it is allowed to cancel. And then we have centimeters here on top. To actually mathematically solve this, we multiply across and then divide. Well, we multiply 8,847 times 100, which gives us 884,700 centimeters, and we divide that by 1, so that's just our answer. Again, dimensional analysis is a methodological approach to converting between units. Alright, the final thing for this unit is talking about matter and density. Now remember, a substance is anything that has a defined and uniform composition. And we have two ways of describing the amount of stuff there is. You have the mass, which is the amount of stuff, and the weight, which is not only the amount of stuff, but also takes into account the gravitational pull. We care about the mass in almost all substances because the mass does not change going from planet to planet or system, from environment to environment, whereas the weight can. Remember that the weight for the moon is about 1/6 that of the Earth, so you're going to weigh 1/6 of your weight on the moon. However, the mass has not changed between the two. Another way to talk about or describe a substance is its density, and this is how much mass there is per unit volume. And again, this is a formula that will be given on your midterm. So density is equal to the mass divided by the volume. So an example would be calculate the density of a piece of bone with a mass of 3.8 grams and a volume of 2.0 centimeters cubed. Just for reference, centimeters cubed. Okay, centimeters cubed is equal to milliliters. Okay, so it would be like saying this was 2 milliliters. But given what we have, we take our mass, which is 3.8 grams, and divide by 2.0 centimeters cubed. And if you divide those, you get 1.95 grams per centimeters cubed. And that is our density. This concludes the first video on Unit 1.